Hi there, and welcome to Chapter 10.3 from Stevens' Introduction to Statistics, the Think and Do book. This is a one-page section, and it's basically describing a hypothesis test that is going on in the background of Table 4. It's not completely necessary to cover this section, but it's fairly interesting if you're so inclined. I can't seem to circle that, so I'll just underline it. Table 4 covers more than it seems, right? So let's take a look at Table 4. What am I talking about here? So here I have, a bunch of sample sizes and critical values of R. So if you have a sample size of, say, 10, and R is equal to 0.751, we look here, and we say, all right, it beats the critical value. We say that correlation is significant. And that's the end of that, right? So we have this sort of magic number that says significant or not significant. And that magic number there's a lot going on behind that. And so that's what this section is basically telling you where that number comes from. There's actually a hypothesis test going on. And we'll suppose that this is rho, Greek letter rho. And we'll assume that's the correlation coefficient between all pairs of variables in a population, right? So it might be 1, it might be, well, it probably won't be 1, but it might be 0, it might be 0.5. We don't know what it is. That's the problem because we don't have the population data. And R, that's the Pearson correlation coefficient, is that in the sample, between the variables in the sample. And we're testing a claim. And that claim is whether or not rho is significantly different from 0. Is rho not equal to 0 is basically what it says. So the claim is that rho is not equal to 0. And we're testing that claim. Right? So the null hypothesis gets the equal to sign. So the null hypothesis is rho equals 0. And so if we get a sample correlation coefficient R, if that's big enough, then what that's saying is we have enough evidence to reject the null and accept the claim that rho is not 0, right? So basically what we'll do is we'd get a p-value or critical values, but the critical values in Table 4 are those that determine sort of the rejection region, right? So if your value of R is bigger than the one in the table, the test statistic is in the rejection region, just like we did in chapters 8 and 9, and you reject the null hypothesis, right? And again, with any hypothesis test, we can choose the significance level, and so Table 4 is generated under a 0.05 significance level on the hypothesis test. Some books will give you tables for 0.01 and 0.10 as well, but 0.05 is pretty standard, so that's the one significance level we have in that table. There are some assumptions, just like in any hypothesis test. The sample of paired XY data is a random sample of independent quantitative data. X and Y both have to be quantitative, and they have to be simple random samples, independent of each other. And number 2 here, the pairs of XY data must have a bivariate normal distribution. And that is not that hard to describe. It means that for any x, for any specific value of x, all of the corresponding y values are normally distributed, right? For any x. And then for any y, all of the corresponding x values are normally distributed. So it's not that hard to explain, but it is certainly hard to prove whenever you have data, right? So the first one we always make sure is met, but the second one, it is difficult to check. What you want to do is you want to look at your scatter plot, and you want to make sure that it looks linear, right? And there are no, big outliers that are messing things up. And so if you get to, if your scatter plot looks like there's a linear relationship and the correlation coefficient says that it's significant, we generally believe it. But so it's always worth looking at it, because checking this second condition is almost impossible. And then another thing worth noting is that a significant linear relationship does not necessarily mean the scatter plot displays an obvious correlation. And what I mean by that is this scatter plot, and I'll get into a second what it is. This scatter plot here, it looks as random as can be, right? It looks like R should equal 0. It doesn't look like there's any linear correlation. But because there's so many in the sample size, there is a linear correlation coefficient that is in fact significant. Right? And so and obviously you'd be hard pressed if you just looked at this raw data. You'd be hard pressed to tell whether it was going up or down. But if you run it through software, it actually does produce a negative regression equation with a negative slope. And what this data displays is something that happened back in 1969 when they were drafting young men for the Vietnam War. And so, they went in waves, first groups, second groups, third groups. And so they determined what order the draftees were taken to Vietnam was determined by a lottery, right? And in that lottery, all the birthdays were thrown into a big bin, rolled around, and then they were selected. And if your birthday got picked first, you were the first one to go. And if your birthday got picked last, you were the last to go. And so I just wanted to show this video because it's a fairly sobering video of the process, and we just don't see things like this very much. So check out this video. This is the draft that actually occurs.
States entered World War II. Tonight, for the first time in 27 years, the United States has again started a draft lottery. And the famous first pick tonight is September 14th, the first birthday that now is designated 001, which means for 19-year-olds born on September 14th, that beginning in January, local draft boards will induct those men born on September 14th, barring deferments. The next birthday in order, April 24th, and so on down the line this evening. This ceremony, which began at 8 o'clock, is now more than two-thirds through. There are 366 numbers to select, one for each birthday in the year, plus one for February 29th, the leap year. The ceremony.
Alright, so that's a fairly sobering video. So when that process was all done, what they had was a set of birthdays, XY data, and the draft order. And what they realized afterwards was that there was a significant correlation. Basically, the later the birth date, the earlier the draft order. Right? So people with late birthdays were very upset about this. The regression line is actually draft order equals, well, there's the y-intercept, minus 0.226 times the birthday, right? If you number these things 0 to 365. So the lower birthdays have a lower draft order. So the question, was this a result of a biased process? Was the process in error? Should they redo it? Or was it just an act of randomness? And there's been speculation, but who knows? But the people spent a lot of time arguing about it, right? It was a pretty severe result, because you were going to Vietnam, and that was not a pleasant place to be. Okay, so that is the hypothesis test behind the scenes and a somber view of a correlation that is not completely obvious by looking at the scatter plot. That wraps up 10.3. We have another short section in 10.4, and then we will wrap up this chapter. See you later.